Alright, so today we're going to be talking about the net force and the elevator problem. Alright, so first thing is, what exactly is a net force? So we have got to address this question before we continue. When a system experiences a net force, it means that the forces acting on it are unbalanced. That's something we've talked about before. When we take the sum of the forces acting on an object in a certain direction while taking direction into consideration, the total force is the net force. So, for example, if we have a 2 Newton force acting on an object to the right and a 3 Newton force also acting to the right, the net force acting on the object is positive 5 newtons, or 5 newtons to the right, shown here. Likewise, if an object experiences 2 Newton force to the left this time, and that same 3 Newton force to the right, the net force this time acting on the object will be positive 1 Newton, or just 1 Newton to the right. All right, so direction matters here again. Basically, if something acts to the left or down or the negative direction, you can pretty much say that that's a negative force. And since these forces act along the same direction, in this slide I'm talking about horizontal forces, we can add them numerically, like integers. So coming off the lab, we have Newton's second law, which states that the net force acting on an object is equal to its mass times its acceleration. So it follows that the net force acting on an object is given by its mass times its acceleration, and the net force of the object points in the same direction. So first up for this elevator problem, let's consider someone standing in an elevator. Now in this case, there's a normal force acting on the person by the floor, and there's a force of gravity acting on the person by the earth. And since they're just standing there, the forces will be balanced because the velocity is constant, the velocity is 0. So for the elevator problem, what we have here is the same scenario, but this time the person is standing on a bathroom scale. Now, the thing is that, and we haven't talked about this yet, but a bathroom scale actually reads you the normal force, not your actual weight, not the force of gravity. And in this video, you'll see that this person is at the top floor, and they will be going down to the basement. So playing this video, this person is going to the basement, and at first they've got at rest, and they weigh about 168 pounds. And in a moment, the elevator starts to move. Notice that the scale gets smaller. The scale reading gets smaller. Then it gets to a point where it's traveling at a constant velocity. We're back to 168 pounds. And then we see that it increases higher than 168 for a moment. So we want to figure out why that happens. Let's play it again, and this time let's look at our motion map. In the beginning, you'll see that we are at rest, which goes with this part of the motion map, these dots, right? They're stacked sideways, and then when the elevator starts to move, we notice that the acceleration is downwards, and the weight actually reads smaller. Constant velocity, no acceleration, same reading as before. And then, when the acceleration is positive, the scale actually reads a larger number. So the takeaway thing here is that whenever you're accelerating in an elevator, the bathroom scale reads a different weight than your actual body weight. So let's take a look this time with our force diagrams. All right, so first up, talking about the force diagram when the person's at the top floor at rest. You'll notice that here, these dots are stacked sideways. Remember, it's a vertical motion map, and there's no acceleration. You're at rest. And because of that, from last unit, we know that the forces acting on you are balanced. The normal force, aka the bathroom scale reading, tells you your true weight, your true force of gravity. Now, when the elevator starts moving downwards to the basement, something happens. The bathroom scale starts to read a smaller value than the person's actual weight. So again, remember, the bathroom scale reads you the normal force, therefore it must have gotten smaller. Notice our motion map. This is the part where we start at rest and we start to speed up. Notice that the acceleration would have to point downwards. Let's look at our force diagram. Notice that the normal force got shorter, right? That's the bathroom scale. Our actual weight stays the same because, after all, when you ride an elevator, it's not like you lose any limbs, you don't lose any mass, so your weight has to be the same. It's the bathroom scale that's changing. So notice which one is longer. It's the downward one that's longer. Which way are we accelerating? Downwards, based on our motion map. All right, let's continue. So now, at some point, perhaps during the first floor, since we're going from the second floor to the basement, we are now coasting. We're reaching a constant velocity for a little bit. So notice the equality lines for my velocity vectors. Velocity is not changing here, okay? And at this point, our bathroom scale goes back to reading the true weight of the person because the forces are balanced. The person's traveling downwards, but traveling downwards with a constant velocity. So if there's no acceleration, neither of the forces are longer than the other. And then finally, we see here that when the elevator is stopping, when going from top to bottom, we see that the acceleration points upwards, right? Our velocity arrows go from longer to shorter to a dot. In order for that to happen, our acceleration would have to point upwards. Now, if we look at our force diagram, we'll see that the bathroom scale reading, aka the normal force, got larger for a brief moment. It's because during this time, we are accelerating upwards, therefore the longer force must be pointing upwards. So that's the elevator problem, and why if you were to bring one into an elevator and stand on it, you should see your bathroom scale reading change. It's because the bathroom scale reading is actually the normal force. It's not your true force of gravity. So the moral of this is just bringing it back to our net force lab and reminding you that if there's ever a case where the forces are unbalanced, the acceleration and the larger force are always pointing in the same direction.